Hi, today we are going to learn about how to compute centroids and moments of inertia, and it's not just going to be about masses. We'll also look at what's meant by a centroid of an area and maybe a centroid of a volume and things like that. So in order to do this thing, you need your ability to do double integrals at least. So this is where really we start integrating over areas and things like that, and not just a simple integral. However, you don't need very advanced versions of it, at least for the problems we are looking at. You need a fairly simple idea of how to do double integrals. Okay, so let's get started. Okay, we are going to look at two aspects from statistics to understand what these things are. The first one is what is meant by mean or average location or average of data points. This represents how accurate we are. Okay, so in our cases, many times we want to be able to replace a large object with a single point. The question is, where should I put it? And that's where we have the idea of mean or average. And the second thing is variance, which is spread of the data points that represents precision. Okay, and both of these ideas I'm sure you have seen, mean and variance. So a small variance means data points tend to be very close to each other around the mean. Right? A large variance means data points are very spread out around the mean and from each other. So this idea of mean and variance you can now generalize to other things. So let's see what we mean by that. So we are going to look at a bunch of masses. You can see that there's a whole bunch of points there. The mass of the ith point is mi, and I want to find out where's the average location and how much is it spread. In fact, we are going to generalize it a little bit. I want to have some coordinate system. There you saw the coordinate system, and I want to be able to find out how much is it spread around the origin here and how far away is the average location around the origin. So there are the points, and the location of any of the position vector of any of the points is Ri, and what we are going to do is compute the average location, which is called R bar. And this has two components in two dimensions, which is x bar and y bar. We put the bar quantities to represent average, and our idea is very simple. X bar is summation xi mi divided by summation of all the masses. It's a fairly simple idea, right? Weighted average. Same thing, y bar is summation yi mi divided by summation of mi, and z bar will be summation of zi mi divided by summation of mi. Weighted average, that's all. Okay, this is a fairly simple idea. Now we don't have to do just that for areas, for masses. We can also do that for areas. You can see here it is summation of xi dai divided by summation of dai. That's the idea. So if I break up any area into small pieces, then I can find the center of mass of this area. Of course, this is where we have calculus to help us, right? Because I don't want to keep dividing this. But by the way, remember this approximate version, because given any area, you can calculate it approximately by dividing it into fairly large chunks and making this kind of a calculation. That's an approximate way, but you can use calculus to get a very precise version. So I'll show you what I mean. So for a continuously distributed values, let us say I have something like this, and I have two curves like that. So this is the left side, right side, top, bottom. Okay, so I have a region bounded by four curves, left, right, top and bottom, and I want to find out where's the centroid. My version is very simple. X bar is integrate x from left to right, and then integrate y from top to bottom of x divided dx. This is the area. And then divide it by 1 divided dx. 1 is just to say that, look, I'm going to compute the area. This is the total area here. Okay, y bar, so x bar equals integral x dA divided by area. Y bar equal to integral y dA divided by area. Okay, the way we compute it is by using iterated integral, that is dy dx. Notice I'm going to do with respect to y first and then x because of the particular kind of problems we're going to do. Which one you do first depends upon what your left and right, top and bottom look like. Okay, now instead of wasting time, we'll just go ahead and try and get some of these things done. For simple curves, so if I have a curve that looks like y equal to x to the n, like this, then this is the base, this is the height, this is the right angle corner. It's pretty easy. Area will be base times height divided by n plus 1, where n is the power. So for example, if I put y equal to it doesn't matter, ax to the n. So if y equal to ax to the 1, which is a triangle, then area will be base times height divided by 2. If y equal to ax squared, which is a parabola, area will be base times height divided by 3, and so on. By the way, rectangle is y equal to a times x to the 0, and then area will be base times h. Similarly, centroid will be from here, how far it is, this distance, x bar from the corner will be base divided by n plus 2. Okay, these are convenient things to compute. Just remember that in case you want to do a quick computation. But remember, it's from the right angle corner, not from here. It's from here. So for example, if you look at a triangle, n equal to 1, so it will be 1/3 of the distance. So base divided by 1 plus 2, which is base over 3. So it is 1/3 of the distance from the corner. If it's a parabola, it will be 1/4 of the distance from the corner. If it is y equal to ax squared, n equal to 2, and so you'll get b over 4. So it's 1/4 of the distance from the corner. This is just a quick idea. Now let's look at a serious computation. Look at this thing. I got to find out where is the centroid of this, and it always involves two steps. First is identify the x and y boundary curves, which means left, right, top, bottom, and then substitute in the integral. So let's look at this thing very carefully, and then we will do the left, right, top, bottom. I'm just going to make sure that my computations are all ready. So here we go. The left side is given by x equal to 0. That's this line. The right side is given by x equal to 8. That's that line. The top is given by y equal to x to the 2/3. That's this line. And then the bottom is given by y equal to 0. That's this line. Once I have this, the value for x bar is given by integral x equal to 0, the bottom to the top, integral y equal to 0 to x to the 2/3 of x dy dx, divided by integral x equal to 0 to 8, integral y equal to 0 to x to the 2/3. Can you see? Top, bottom, top, left, right, dy dx. So if I do this integral, it will turn out, I will get this is equal to integral 0 to 8, do the inner integral first, and you'll get x to the 5/3, and then the bottom will be integral 0 to 8, x to the 2/3 dx. You can mess around with it. You will see that that's the deal, and then the resulting equation will turn out to be turns out to be 5. Compute it and see. Okay, This is the inner integral, that's the inner integral, and you can see how this works. Okay, and you'll get the answer. It's not a complicated thing. Okay, fine. Now let's look at so that tells you that it's about 5 units from here. Of course, this is of the form y equal to x to the n, and you could have found out that x bar is base, which is 8 divided by 2 plus 2/3, and that will turn out to be 3, which is from here. 3 units from here is 5 units from there. Right? Now let's compute. So that tells me where the x bar, this distance is. Now I want to find out where is y bar. What about this guy? Let's do that next. And same idea. We know the left, right, top, bottom. Y bar equals integral the left side x equal to 0 to the right side x equal to 8. The bottom y equal to 0 to the top y equal to 2/3 x to the 2/3 power. This time I'm going to do y dy dx divided by integral x equal to 0 x equal to 8 integral y equal to 0 to x to the 2/3 dy dx. This turns out to be, you can compute this, and if you do that you will get 10 over 7. Oops, sorry. 10 over 7. You're with me? So I do y dy first, and I'll get y squared over 2, apply the limits, and I'm not going to explain how to do the double integral, but I'm just going to show you how the method works. Okay, you can do all the details by yourself and you will see how this works. Got the idea, right? Now let's look at something a little bit more complicated. In this case, I have to do again same thing. Let's do left x equal to 0. That's this line. This line is the other one. Right x equal to 1. Top x equal to 2/3. Bottom x equal to 3/2. Sorry, x to the 3/2. Y equals x to the 3/2. Okay. Now x bar equals integral x equal to 0 to x equal to 1, top to, so bottom to top, and then sorry, left to right, and then I'm going to integrate bottom to top. So bottom is x to the 3/2, top is x to the 2/3. This is y equals. So I'm going to do x dy dx. So notice when I'm doing x dy dx and I'm going to integrate with respect to y, it's just going to be, whoops, it's just going to be xy. So it's a fairly simple integration, and I'm not going to bore you with all the details. You will have to know how to do this. Y equal to x equal to 3/2 to x equal to 2/3, x to the 2/3 of dy dx. Right? So you just have to integrate these two things, and when you do that, you will get the other version, which tells you that this is 25 over 56. That's it. So in case you are confused about how to do this integral x dy between the limits x to the 3/2 and x to the 2/3 equals xy between the limits x to the 3/2 x to the 2/3, which is x to the 5/3 minus x to the 5/2. Right? That's what goes here. And then integrate it with respect to x again. Got it? That's how it works. Okay, that's all you need to do to find centroids. But there is a shortcut. Most of the time, you're not going to be dealing with funny shaped centroids. This is rare situation. The more common situation is the following. You got some shape